Okay, let's finish up our conversation about area under the curve and Riemann sums and the limit process. And I promise it'll get easier to take these definite integrals as we move along. Just a quick note on notation. I'm in the habit of using the notation I learned, in different textbooks will use different things. I just use I here. Okay, so you might notice how that's different. And this, as the width, if you want delta x, goes to 0, what's also happening, the number of rectangles goes to infinity. So those are the same. Think about those as the same. Here's my notation from the last video. That's not my notation. This is I, always I, or your book uses K, same thing. I equals 1 to n, same as here, only they're using K. And then instead the limit as delta, the width of the rectangles goes to 0, the number of rectangles goes to infinity. So that's the same, just a different notation. And then instead of x sub k, I use x sub I, and I don't use the little star. I'm keeping mine simple in that it has to do with the uniform width, and that goes with this as well. The width of these in a Riemann sum could actually be non-uniform. That is, some widths could be different. And then as you take the number of rectangles to infinity, it doesn't matter that the widths are different. So I'm keeping it basic. I know what you're thinking. It doesn't seem basic because those are complicated problems. But I'm just keeping all my examples as a uniform width, which is just delta x. That's just the difference in the interval broken up by n. Okay, so if you see that in your text, don't be scared. It's the same thing I'm doing in my videos. And this is the definition of, and this is the more important part, this is the definition of a definite integral. Right now, we're going to have a better definition later. It's called the fundamental theorem of calculus. It's going to make this, it's going to say, okay, we did this once, we don't have to do it again. Okay, so we'll have a better way. I keep promising you that we'll have a better way to calculate area under the curve and definite integrals when we get to that in the next section. All right, but first we're gonna work with those. So we're gonna need some properties. So let's talk about net area. What does it mean to have a net area? So area for us in geometry has always been a positive value, but now we kind of think about area because we're connecting it to this definite integral. So we're gonna have to deal with negatives. So let's take a look. So the idea here, and here is your process again, where you'd have n rectangles and then you take them to infinity. The idea here would be that this is positive, which makes sense to us, that's area. This is positive, that makes sense to us, this is area. But this would actually be negative, which we wouldn't really call area, but we're going to use a net area idea, and that this is a negative area. So, and that should make sense because if you think about it, the widths would all still be some delta x value. And the heights, if you plugged in f of some x value in here, it's going to give you a negative output, right? So you'd have a positive times a negative, which is a negative. Okay. So if I asked you to do, well, let's look at one. So this is as n goes to infinity, we would have that. Let's look at one. Let's think about this. What if I said, okay, so figure this out based on this picture. See if you can get the answer. If I say, find the definite integral from 1 to 6 of this function, 2x minus 6 dx, what do you get? Pause the video, give it a guess, see if that makes sense. So you would have, I mean, they're giving you the area, but you could do this by geometric because this is a triangle and this is a triangle. And it wouldn't be 4 plus 9. So this is area 9, this is area 4. But because the idea of net area, it's under the x-axis, it's going to be negative. So it'd actually be negative 4 plus 9. And you get 5. Okay, so that's the idea of net area. If it's a negative, if it's under the x-axis, it's negative. Okay, and then once we find, and if we did this by the Riemann sum process, it should work out because all of these outputs for my f of x sub i's are going to be negative. And then once we get to this method I keep promising you about using antiderivatives, when we integrate that, it'll give us that number. Okay, it'll consider the negative function values as well. All right, so same idea here. What do you get? If I integrate f of x from a to d, it would be 12 minus 10, right? We wouldn't add the 10, plus 8. And that gives us 10. Okay, so that's one property of definite integrals. Here's a couple more. Think about this one. You have a function, you're starting at a, and you don't go anywhere, then the area is 0, right? That's kind of a weird one. You won't see that much. This one you see every once in a while, and I'll just leave this without a proof or anything. I won't prove everything in here. You just have to kind of take my word for it. If you think about it, if you work with this one, it'll make sense. We'll get into these later. But if you're going from B to A, which just looks kind of weird because usually it's A to B. So in other words, if you're doing some work, and this will come up later, and you end up with like something backwards, that should look really weird to you. You say, well, wait a minute, I'm not integrating from 10 to 5. What I like to do is integrate from 5 to 10. But it turns out this is actually the opposite of what you would get. That is, if I want to flip these bounds, I'm allowed to do it, but I just have to make the whole thing negative. All right, and then here's some other properties that should make sense, I think, if we're talking in terms of area, and this would be true if it's a negative area down here, that if you integrate from A to B, you're allowed to break up this interval, okay, or the integral, both are true. You're allowed to break them up and just go from A to P, and then add that from P to B, and that would be the entire area. Pretty straightforward. So if that one works, then the negative one has to work as well. If you have this large area and you take away a smaller, you should be left with this section right here. Okay. Net area. So if you go from A to B, the net area under the curve, if the function is always positive, this one should make sense too. If the function is always positive, then the net area will also always be positive. That just has to do with if everything's above the x-axis. Okay, so when you do your homework, let me bring your homework in real quick. Let's see, I think we can handle all of these now. So this is using geometric, that's just a rectangle. If you know your formula for the area of a triangle, you should be able to get this. This has to do with that net area. So what I would do for this one is figure out which is the right picture, and then negative, positive, right? Add or subtract them, or add the negative to the positive to get your value. It looks like it's definitely not going to be that one. It looks like it's going to be one of these, and the answer should be negative, right? Because the area of the negative triangle is bigger in all those cases. So that's using some geometry. This one, if you look at the graph, I think you might be able to figure this out using the concept of net area. So I would just graph these. Using your property. So if you want to subtract them, this one's straightforward. If you go from 1 to 7, the difference, you just break it up. So it should be this one, right? It's just 2x cubed from 1 to 7 minus 3x from 1 to 7. This one, sorry, I'll make you do the, this will be a longer one. I'll make you do the sum of all the rectangles. So that's more practice with the approximation. Should be negative. Same idea with that one. And then here, you're just using the geometry to estimate. Okay. So you'll notice I'm taking it easy on, and this just deals with some of the properties. Constant multiple property. Oh, I think I forgot to tell you that one. Yeah, why wasn't that in there? Let me see. Yeah, so constant multiple. This one's pretty straightforward. So a constant multiple property would be, I don't know what happened to this one. That is, if I have a constant times a function over a definite integral, And this one actually you use a lot, but it should be straightforward because we knew this about limits. You can pull the constant out of the integrand. And that's more of like an organizational thing most of the time, just to keep your work separate. Okay, so you'll notice that I'm not actually making you do the limit process. That is, I'm taking it easy on you a little bit. I showed it to you. It's in the videos. But if I ever ask you to do like you can't do this by estimated geometrically. You can estimate it. Did I say estimate? You can do this. Oh, you cannot do this by a geometric shape because it's a parabola and there's no such thing. You can't get a triangle or trapezoid. You can estimate it. I will make you do this. You can estimate it using 5 minus x squared would look something like that. Maybe 4 rectangles or something on some interval. I will make you do that, the estimate. I could ask you to find the exact value by using the limit process. And let's say it's over 0, 1. And that would be f of x sub I. And the width would just be 1 minus 0 over n, which is 1 over n. And that's the process I worked through in those examples that you hopefully watched. And it's very long and very tedious. And it takes a lot of work, and then you get the answer. But I'm not going to make you do that. In a 15-week class, I'd probably make my students do it. I don't think you're going to need to do stuff like this in the future because, like I say, once you learn the easy way to do this, that's what we're going to be doing. So I just wanted to give you some exposure to it, but I'm not going to actually make you do the long process in order to find that limit. Okay, so I hope all that makes sense. And if you ever have questions or want to meet, just let me know.